Thank you. Hi, my name is Sang-Hyun, a graduate student at Seoul National University. In this talk, I would like to present a precise Hausdorff distance computation algorithm for freeform surfaces. This is a joint work with two other authors. Hausdorff distance, or HD, measures maximum deviation between two objects. One-sided HD from A to B is defined by the maximum deviation of A from B. Then, two-sided HD is just the bigger one among the two one-sided HDs. HD is a good candidate to measure similarity or difference between two objects. Our work is based on matching technique originally proposed by Kim et al. However, they had limitations in handling cross-boundary problem and polar points problem that arise when precision goes up. For instance, they had limitations in handling cases where this matching occurs at the boundary or corner. By handling these problems, we improved the precision to machine precision. These figures show the cross-boundary problem. We handle this problem and get stable result using osculating toroidal patches. Kim et al.'s algorithm was the first CPU-based algorithm to compute near zero HD in interactive speed. We also compute near zero HD using the same Utah-Tipan model and achieve machine precision in interactive speed. Kang et al. Also succeeded in computing high-precision near-zero HD between mesh models using matching technique without much additional cost. Since they dealt with polygonal meshes, they could handle cross-boundary problem easily. The left graph shows the result of Kang et al., and the right one shows that of ours. Kang et al.'s result shows that computation time does not change very much. However, our result shows that more computation time is needed as precision goes up, since we handle freeform surfaces. After we obtain high-precision HD, as shown in this graph, we can use Elber and Grandine's solution for machine precision HD. This is the outline of rest of my talk. After related work, I will introduce toroidal patch and how to use the toroidal patch to compute lower and upper bound of HD. After that, I will summarize the overall algorithm, present experimental results, and conclude this talk. There have been many previous results on computing HD between two polygonal mesh models. Mesh and Metro are popular tools to compute HD. After that, Tang et al. And Barton et al. Succeeded in computing interactive and precise HD. As stated earlier, Kang et al. Proposed an algorithm to compute near-zero HD with high precision. In the case of freeform surfaces, Elber and Grandine have computed precise HD. Krishna mostly devised a GPU algorithm using AABB3. Haniel also proposed a GPU algorithm for near-zero HD. At last, Kim et al. Came up with a CPU-based real-time algorithm to handle near-zero HD. Now, I'd like to introduce toroidal patch that we use. We can generate toroidal patch with second-order contact. When curvature is positive, we can use outer part of torus. When curvature is negative, we can use inner part of torus. This is a sample image of toroidal patches that approximate a Utah teapot very precisely. By placing these toroidal patches in the lymph nodes, we can build a hybrid BVH based on toroidal patches. Now, we can use this BVH to compute bounds of HD. First, we can compute the lower bound of HD with this BVH. In the overall algorithm, we compute this lower bound. To be specific, by projecting a point to the toroidal patches, we can find the lower bound of the minimum distance from the point to the model. Imagine we sample a lot of points from each model and finding the lower bound of minimum distance from them to each other model. Then, we can use the maximum value among them as the lower bound of final HD. We can also compute the upper bound of HD, shown in the right. We compute the upper bound by matching technique. We match a point on AK to a point on BK using simple reparameterization technique. If we reparameterize BST, we can see that the maximum distance between the matching points is the upper bound of the one-sided HD from AK to B. We uniformly sampled these matching points and added approximation error to estimate the maximum value. However, this matching technique fails when AK stretches across multiple different surfaces that have different parameters. As stated earlier, if not careful, this may generate too many recursive subdivisions of AK. We call this problem cross-boundary problem. We could handle the problem with toroidal patches in the lymph nodes. First, we collect corresponding surfaces of B to AK. Then, we prepare osculating toroidal patches for the surfaces by loading them from BVH or generating them on the fly. By subdividing TA recursively and projecting sample points to other patches, we can estimate the upper bound of HD. Since we use toroidal patches, it is much more efficient to subdivide the patches and project points than original surfaces. We could handle the cross-boundary problem in this way. Now, let me introduce the overall algorithm. As we have seen before, we can find the lower bound of HD by sampling points on one model and projecting them on the other one. We can also find the upper bound of HD by partitioning a model and finding matching in the other model. Therefore, we can maintain these bounds of the final HD during the algorithm. Also, we maintain a priority queue that contains nodes from both BVH. Then, we can pop an item from the queue and update the bounds by investigating the child nodes. After some updates, when the difference between the bounds becomes less than the specified error bound, we can terminate the loop and report the result. However, if a user wants to compute precise HD, we can convert to the numerical solution of Elber and Grandine by using all the remaining nodes in the queue as initial points. Now, let me show you the experimental results. We used three kinds of freeform surfaces in the experiments: general surface, surface of revolution, and surface of linear extrusion. This figure shows the result of precise HD computation. You can see that the error is less than the machine precision and the computation time is not so long. In this video, we compute the HD between identical models in different configurations. You can see that our algorithm runs very fast. In case of surface of revolution and linear extrusion, we can perform real-time deformation and HD computation. This video shows the HD computation between deforming surfaces. You can see that our algorithm computes HD in real time for the deforming surfaces. In the experiments, we computed HD for identical models in many configurations. We can see that the bounds converge and computation time increases as precision goes up. However, you can see that the increase of computation time is not that significant. Let me conclude my talk with three main contributions of this work. First, toroidal patch is crucial as it has good properties and provides a solution to the cross-boundary problem. Second, we could compute the precise HD without significant increase of computational cost using these toroidal patches. Finally, we could compute HD between dynamically deforming surfaces of revolution and linear extrusion in real time. This is the end of my talk. Thank you for your attention.